Hello everyone, still under entropy. Now we are going to discuss how we can calculate total entropy of a given reaction. Now, calculating total entropy is just knowing entropy of a system and that of the surrounding, then joining them together. Now, if I want to do such a calculation, I know maybe you've been given us data that you don't know how to deal with, and you are asked to calculate total entropy of a given reaction. I'm going to give you the formula that we're going to use whenever you're told to calculate total entropy. What you're going to do is you're going to get total entropy now. That's the formula that we use whenever we want to calculate total entropy. Now the key thing that you have to know here is that in any chemical reaction, a reaction is taking place in a given space. So if that reaction is taking place in a given space, the surrounding upon which that reaction is taking place will be affected by the heat energy produced or absorbed by that given surrounding. And entropy of the system is just the particle undergoing the reaction, and we need to know the relationship whenever we are trying to calculate total entropy of a given reaction. So that's the formula that we use whenever we are calculating total entropy of a given reaction. Now, initially I had taught you how to calculate entropy of a system, and we had already done calculating entropy of surrounding. Now, I'm going to give you a sample of a question that is going to help us understand how we can come up with the calculation. Now, I'm given a reaction here, and the reaction I'm going to give you is the same reaction that we did initially. Imagine hydrogen gas reacting with an atom of oxygen to give us a mole of water. And we are told this reaction is an exothermic reaction, and the delta H is negative 286 kilojoules per mole. Now, if I'm supposed to calculate delta H or delta S of the system, what I'm going to do is I'm going to say my delta S of the system under standard condition is equal to summation of the entropies under standard condition of the product minus summation entropy under standard condition of the reactants. So in such a scenario, I'm going to have a situation whereby if I'm to calculate delta S of the system, I'm going to have a situation whereby I need entropy of the product, which is water molecule in liquid state, minus the entropy of hydrogen gas minus a half, because I used only one atom of oxygen, entropy of oxygen gas. Now, if I fix the values according to the data that I gave you initially, you'll realize that my delta S of the system is going to be 69.9 minus 130.6 minus a half of 205. Now, if you do that calculation very well, our delta S under standard condition of the system is going to be 163.2 joules per Kelvin per mole. If this is what we are having as our entropy of the system, now we can go ahead and calculate entropy of the surrounding. Can go ahead and calculate entropy of the surrounding, because we need that entropy of the surrounding, which we are going to add at the end of the day. And now, in calculating, I'm going to use a different color so that we can get the difference. In calculating entropy of the surrounding, we agreed that we are using negative enthalpy change all over temperature. And assuming that this reaction is taking place under standard condition, which is 298 Kelvin, so I'm simply going to have a situation whereby the reaction is taking place at 298 Kelvin, is a standard condition. I'm going to have the enthalpy for the whole reaction that was given to be 286 kilojoules per mole. So I'm going to have a negative of negative 286 all over 298. So if you do that calculation very well, you do your calculation very well, you'll come up with a total of that. And when that happens, you're going to find that now you are going to have our delta S total to be delta S of the system plus delta S of the surrounding. So when you do so, we're going to have a situation whereby we got a negative value there. So we are going to have minus 16.3.2 joules per mole plus 960 joules per mole per Kelvin. So to explain further how I arrived at this answer is simply, this one was given in kilojoules per mole. This is K. So because the negative and the negative will cancel out, I'll have a positive value. Then I multiply this by 1000. Is when I divide, I'll get to 960 joules per Kelvin per mole. Then my total entropy of that given reaction is going to be positive 796.8 joules per Kelvin per mole for that given reaction. So that's the same procedure you are going to follow for each and every type of question that you are going to be facing whenever you are calculating total entropy of a given reaction. You have to know very well that in calculation, you have to determine the entropy of your system and the entropy of the surrounding. Then you get a summation of both. That one will give you total entropy and a standard condition. And as I said earlier, the standard conditions here are standard conditions are a temperature of 298 Kelvin, a pressure of 1 atmosphere. And mostly we always treat a mole of each and every reactant, which can sometimes vary due to the amount of substances that are taking place in a given reaction. So this one doesn't really matter, but sometimes it must be considered if you are dealing with same values or having same concentrations. But if the concentrations are not the same, ensure that the reaction is taking place at room temperature, pressure, and a pressure of 1 atmosphere. Thank you very much. Have a wonderful time.